In this video, I will show how to use two different voltage regulators to create a power delivery system for your circuit. So the first things first, what is a voltage regulator? A quick Google search will tell us a voltage regulator is a system designed to automatically maintain a constant voltage level. What this means in practice is that we can give a variety of voltages to our voltage regulators and get a steady output voltage. The input can even vary, such as in the case of ripple voltage. One thing I should note is that the input voltage needs to always be higher than the expected output voltage. We'll get more into that later. Voltage regulators aren't the only way to change one DC voltage to another voltage. They aren't even the most efficient. Voltage regulators are part of a class of circuits called DC to DC converters. Another notable type of DC to DC converter is called a switched mode power supply. The circuit is much more efficient than a voltage regulator. We'll get into efficiency later. So if switched mode power supplies are so much more efficient, why are we using a voltage regulator? Well, there are three reasons. The first is a stipulation I set when I first started this robot. I'm not using any breakout boards. The second reason clarifies that a voltage regulator is sold as a single electrical component. Switched mode power supplies are much more complicated circuits. As a result of this, they're typically sold as a breakout board, and I don't fancy the idea of having to design that entire circuit myself. The last reason is price. Where voltage regulators reign supreme is cost. Most voltage regulators are cents on the dollar, whereas a switched mode power supply can be much more expensive. Now that we've got our decision rationale out of the way, let's get on to our circuit. If you'll recall from the last video, we have two voltage rails we want to create, a 5-volt rail and a variable rail to control the speed. We'll start with the 5-volt regulator. For the 5-volt regulator, I decided to go with the L7805. Let's take a look at the data sheet here. We are looking for the following in this data sheet. We want to find the input voltage range, we want to find the maximum current output, we want to find example circuits, and we want to find the pinout. So we see right here the first line is an output current of up to 1.5 amps. So we've got that one. If we scroll through here, now we've got the pinout right here. So if we're looking directly at it, our input voltage, which we've still yet to figure out, will go in this first pin on the left. Then the middle pin is ground, and then the right pin is our output, which will output our steady 5 volts that we want. Now right here under maximum ratings, we can see that our DC input voltage is going to be between 5 and 18 volts. Realistically, we don't want to go as high as 18 volts, so we should be good there. And then we've got an example circuit right here. So as you can see, it's actually a really simple circuit. Our input is going to have a connection from there to our ground pin via a capacitor, a 0.33 microfarad capacitor, and likewise there's going to be a connection between our output pin and ground via a 0.1 microfarad capacitor. That's really all there is to it. From there you just connect your input voltage here, you connect this to your rail so you can pull your 5 volts wherever you want, connect this to ground, and you're good. So with that, we have everything we need to start building our circuit. So I start by putting my 5-volt regulator in the breadboard here. Then I put a 0.1 microfarad capacitor between the output and ground. Next, I put a capacitor between my input and ground. Now in the circuit, this is supposed to be a 0.33 microfarad capacitor, but I couldn't find one of those, so I used a 22 picofarad capacitor. This will be correct in my final design, but for now this will work. Next, I connect ground to my middle pin, and I was supposed to connect my input pin to the voltage rail here, but as you can see, I accidentally connected it to ground. I'll realize this later and correct it. Next, I'm inputting my power here. This is going to be 9 volts, which I'll show you in a minute. And then I pull out my trusty multimeter. I have it set to voltage mode here so I can take the readings. The initial reading is 0 volts because my power supply is not turned on yet. Turn on my power supply, and now I get 9 volts approximately out of my power supply. Next I go to measure from ground to the output, and you'll notice it's 0 volts because I forgot to connect my input to the correct voltage rail. After realizing this, I correct it. And now we take a new voltage measurement from ground to our output. And it is a steady 5 volts here. So we just stepped down from 9 volts to 5 volts. I mentioned that I wanted to go with a variable voltage regulator in order to control the speed of my motors. For that, I decided to go with the LM317T. In order to design my circuit, I need to know the input voltage range, the output voltage range, the maximum current range, example circuits, and the pinout. So if we look here, right on page 1, we've got our output voltage range of 1.2 to 37 volts, which we can tune to what we want. We've got output current, it says in excess of 1.5 amps, so we want to stay well below that 1.5 amps. Scroll down a little bit. On page 2 we see our pinout. So if we're looking straight at the pin, the left pin is going to be our adjust pin, so that's how we control our output voltage. The middle pin is going to be the actual output voltage we want, and then the right pin is going to be the input voltage. Just like with the 5 volt regulator, the input voltage has to be higher than the output voltage to get the output voltage that we expect. We scroll down a little bit more. Now we're starting to see some different electrical characteristics in the schematic of the regulator. Now we're going to look for now we want the electrical characteristics for the 317, the LM317. So that's the 217. And here's our 317. So we can see our voltage in to voltage out delta is 3 to 40 volts. So we want to stay well below that. We should be fine because we want to put in about 9 volts. So we'll be good there. Scroll down a little bit more. There's a lot more electrical characteristics. And here is our basic circuit right here. So this is our voltage regulator. We just put the input voltage in straight into the regulator. Nothing fancy there. Then we have what's essentially a voltage divider between our outputs and ground. And what makes this so magical is that voltage divider is going into the adjust pin. So R1 will stay a constant voltage, then R2 we can put a potentiometer to, which we can change the resistance of the potentiometer, which therefore changes the output of the voltage divider, and in turn changes the output of the voltage regulator. Another thing that we want to know is this equation right here. Now we're not really going to use this in this design, but it's important to know. This explains how to calculate your output voltage. Now that we have that information, it's time to design our circuit. Like we learned in our example circuit earlier, the output voltage is basically set with a voltage divider. I'm going to use a potentiometer on one side of that voltage divider to allow me to adjust my output. On the other side of the voltage divider, I'm going to use a 330 ohm resistor here. This is mostly an arbitrary decision. It all depends on the range of voltages you need and how much current you're trying to restrict. We now have all of the values we need to test our circuit, so I'm going to build it on the breadboard now. So I start by putting my voltage regulator in my breadboard. From there, I put a 330 ohm resistor between the input and the adjust pins, pins 1 and 2. Next, I connect the output pin directly to my voltage rail. And lastly, I put a potentiometer on the adjust pin. So one of the outer legs of the potentiometer is connecting to the adjust pin and to the resistor, and then the middle pin is going to connect to ground. So the resistance will change as I turn the potentiometer. Now I should note, in my final design I want to use a 10K potentiometer to help get a bigger voltage difference, or voltage range. This potentiometer is a 1K potentiometer, so I'm not going to get as much of a voltage difference, voltage range as I want out of this demo, but it still works nonetheless. Next I pull out my trusty multimeter, and I connect my multimeter directly to the input and the ground and output rails on my regulator here. There's my ground reference. Turn it on and I don't get a voltage output because I haven't connected my power supply yet. My power supply is still set at 9 volts. And now when I turn on my power supply, you'll notice I'm getting about 3 volts. If I change the potentiometer, which was really hard to do at this angle, you'll notice I get a range of values. Go from about 1.5 volts up to about 5 volts with these values right here. Like I said, this is not the potentiometer I want to use in my final design, but it works as a demonstration. Now that I'm confident in the operation of this circuit and my 5-volt regulator circuit, I'm going to add them both to my main board. So now, when I add my voltage regulators to my board, I start with my 5-volt regulator. I wired up almost the exact same way. I didn't notice this when I was wiring it up, but I actually had some of the connections shifted to the right. So when I powered it up, I kind of drew a lot of power initially and almost got the magic smoke. This voltage regulator still works, and I managed to fix the issue. But you'll notice when I'm initially wiring it up, some of the things aren't plugged in the correct spot. Now I flip it around to do the other side. Here's where I'm going to put my linear voltage regulator. Now I have them offset from each other because that way I can put heat sinks on them. I have the heat sinks with me, I didn't put them on this video, but I'm going to put them on soon. And this allows me to draw more current through them without fear of blowing everything up. They dissipate a lot of heat at that point. The linear voltage regulator I wire up pretty much the exact same way as I showed you earlier. Next, I need a place to connect my input voltage of 9 volts. Since I'm already using 2 voltage rails, I'm going to draw it off to a row of pins. So first I connect my 5 volt input into that same row where I'm going to be putting my 9 volts. And then I connect my linear voltage or my adjustable voltage input into that same rail. Now as I plug things in, there's two major things that are going to go wrong here. The first is that I'm plugging my ground of the power supply into one of the ground rails, which is fine. But my ground rails aren't connected. They're electrically isolated at the moment, which means only one side is getting ground. The other thing is, like I mentioned earlier, on my 5-volt regulator, I have something shifted 1 up. So when I turn this on, I'm not going to get what I want out of this. In fact, you can't see it, but I could smell something starting to burn, which is when I very quickly pulled the plug and went back, debugged it, and figured out what was wrong. So I probed it here, realized I forgot to turn on my power supply, and went and turned that on, and probed it again. Now I'm getting 9 volts out of this, which is what I want. But when I go to probe my output, I get nothing, and I very quickly pull the plug because I realize what's going on, that somehow power's not right. I'm touching them, I feel all the heat coming off of the 5-volt regulator, so I know that was what the problem was. So it took a while, but I figured out what the problem was and rewired it correctly. Now I have everything plugged in, and I'm about to turn on my power supply. After I do that, I'm going to probe around a little bit. So my output here is 5 volts, which is what I expect. It's hard to see, I apologize for that. My output for my linear voltage regulator, or my variable, was about 5.1 volts, so I changed the potentiometer a little bit. And now I get about 3.9 volts. Earlier I was talking about efficiency. As it turns out, the efficiency of a linear voltage regulator is pretty simple to calculate. It's given by this equation right here, which is basically your power out divided by your power in times 100. As you can see, the voltage delta between the input and the output determines how efficient the circuit is. The greater the difference, the less efficient the circuit is. This is why just because you can power the 5-volt regulator with 18 volts doesn't mean you should. I recommend trying to keep your input voltage somewhat close to what you're expecting to get out. This also means that the slower a robot is going, the less efficient the circuit is, since the input voltage is steady, but we are controlling the speed of the motors with a varied voltage output. As always, I'll have links to all the datasheets and parts I used in this video in the description. While you're there, please consider subscribing. I really enjoy making these videos where I walk through my design of circuits, and interaction really helps me know if these videos are effective or not. With everything that's going on, I hope you are all doing well. I'll see you in the next video where I finally get into designing the chassis for this robot.